Welcome. It's great to see familiar faces and some new ones on here. We're very excited to have all of you joining us and to have Dr. Barbara Natterson Horowitz here with us. We've been talking to and working with Barbara for a long time, and I've brought her work to the Ask Nature Biomimicry crowd in a couple of ways, and are really excited for this in-person dialogue-based experience that we can have today. We've got people coming in. This has been one of the really fun things since launching the Ask Nature Hive community and doing more of these events. We're really seeing the biomimicry community from around the world popping up and getting to all be in at least the same virtual space in a new way. There's a lot of great opportunities for a lot of collaboration and conversation within this community. And we're happy to be bringing more opportunities for that to happen to the fore. So people will be able to continue joining in. This is an open Zoom link. So as they get their alerts and come on in, everyone is welcome to join on in. Feel free, everyone here, to be on screen or off throughout, or when you're asking questions later. We ask that everyone keep their mic muted in the meantime. So this is just a few of the things to keep in mind. If you have questions for Dr. Natterson Horowitz, please use the Q&A button, which is down at the bottom of the screen. Off to your right, you'll see a little Q&A button. Our staff is monitoring that and be watching and communicating and sharing those questions and queuing them up for us, so that we'll be able to hopefully give everyone a chance to ask their question. They'll liaise with you in the background and see if you'll be happy to be on screen and ask your question live. That's great if you can do that and really engage there. If not, don't worry, I can read out loud, and happy to represent your questions, giving your name or just as an anonymous question. Happy to do that. So whatever you have questions burning in your heart for our cardiologist here, feel free to ask. So use that Q&A. There's also the chat section where you can just chat and be talking to each other. It's great to see in there kind of a cascade of info about where people are calling from, maybe how they've found this event, or anything you'd like to share, any welcome to each other. Just great to bring that sense of community alive in our experience here. This is really our hopes and dreams for the Ask Nature Hive and these live speaker series conversations that we're having, is that it gives us this opportunity to not just be broadcasting, but to be really engaging and opening up a dialogue and really bringing this global community together around wonderful topics and individuals, because each one of us is a wonderful bee within this hive. And our queen bee today is Dr. Barbara Natterson Horowitz. Okay, so Barbara is a cardiologist and evolutionary biologist on faculty at Harvard University, Harvard Medical School, and the University of California in Los Angeles. She's a New York Times best-selling author of both of these books. You can see Zoobiquity, co-authored with Catherine Bowers, and its follow-up, Wildhood, which explores the connections between human and other animal adolescence, which is really exciting. And we'll explore all these ideas with Barbara today. Some of these have already come to the biomimicry community and the Ask Nature audience through this collection that we worked on early last year, which is now almost 2 years ago, The Sisterhood of Species. And in here, Barbara kind of outlined her work. We brought together a lot of the key features and that she's looking at within our other fellow animals species, and the ways that we can learn from them in a collection, some new illustrations bringing these ideas to light. So feel free to explore that following this event if you haven't. And now, without further ado, I'll hand off to Barbara. Welcome, and welcome on behalf of the Institute and this whole community.
Thank you, Andrew. It's really been a privilege to interact with Ask Nature. I discovered you kind of just serendipitously and am a major fan. So this is just a privilege to be here today. I'm going to just jump in and start, and my story is kind of baked into the presentation itself. So just a sec, and here we go. All right, good. Andrew, are you seeing this? I can't see you.
Everything looks good.
Okay, so if there's any technical issues, since I'm not seeing you, just holler and that'll let me know.
Will do.
So wonderful. Today I'm going to spend no more than 30 minutes, maybe 33 minutes. I'm going to go quickly because really I want to have a conversation and talk about human health insights from across the tree of life. So for the past 15 years, I have been working and doing research that's all based on a single idea. And that is that the field of medicine is very anthropocentric. And that apart from a handful of model organisms, we basically, and by we, I mean physicians and the world of medical education, we really focus on humans as the center of health. But I'm not sure that's such a good idea. And in fact, I think that if we could open the window through which we perceive health and illness to include at a minimum, over 30 million metazoan species with whom we currently share the earth, the extant species. So if we could do that, and then if we could open that window even wider to include the evolutionary history that has shaped those similarities and differences we have with these other species, and that evolutionary history is depicted by this phylogeny embedded in here, that if we could do that, I wonder, I think, I actually believe, we could do a much better job understanding why we are vulnerable to so many diseases. And we could really do a much better job at innovating effective solutions and strategies to prevent diseases. In other words, to work toward being more resistant and resilient. Now, those are some big claims, and I think I now have maybe 32 minutes. And so here's the plan for this morning, or rather this afternoon. I'm going to quickly tell you about my journey, do a brief kind of evolution 101, talking about how I apply some evolutionary principles to my work, and then really launch into the two sides of my claim. One is that this phylogenetically wide and this broadly comparative and evolutionarily informed approach can help us understand vulnerability. And I'll have two clinical examples, one which is from cardiology and the other which is breast cancer. And then I'll really jump into what I think should be of greatest interest to this crowd, which is the idea of resistance, of looking at the evolved adaptations of other metazoan species as a source of insights and knowledge that can be clinically, ultimately translational, a source of translational insights for clinical medicine. And I'm going to start with heart failure, talk a little bit about gestational hypertension, osteoporosis. You can see that there's an emphasis on women's health here. But as I'll share, this approach can be applied across all pathologies. And then we're going to have a conversation about this and the future. Here we go. So my journey, in a nutshell, I started my career as a physician and academic cardiologist, a professor of medicine. I did my cardiovascular fellowship, followed by advanced training in heart failure and cardiac imaging, and was, kind of a pretty typical academic cardiologist until 2005, when the Los Angeles Zoo asked if I'd become the cardiovascular consultant, first for their great apes, but ultimately I expanded the work I was doing there to include a wide range of species. And over the course of maybe 5 to 7 years, I really, my eyes were opened to a tremendous amount of really a perspective that I hadn't encountered before. One of the first cases that I saw was a chimpanzee who they thought it had a stroke. And I remember I put the probe down, and what you're seeing here is it's an echocardiogram, but the probe is, we put it into the esophagus. And these are the 4 chambers of a chimpanzee's heart, the animal I was examining: the left ventricle, the right ventricle, left atrium, right atrium. And you can probably see, I hope you can see these kind of bouncing collection of echoes there. These are blood clots. And the moment I saw this, it reminded me of an echo that I had done on a human patient months before. And it turned out they had the same form of cardiomyopathy that induces hypercoagulability in blood clots. And so this was sort of, in the beginning, a great surprise to me. I say with some embarrassment, but I think it's important because I think it's important to know where the kind of work that we need to do to bring together the fields of human and animal medicine. In any event, I saw all kinds of diagnoses in great apes and other animals. And over the course of this period, I became quite interested more and more in how I could use this experience and this knowledge to improve human health. Of course, I'm not the first physician to recognize this very important connection between human and animal health. Virchow himself, father of modern pathology, in the 19th century wrote, "Between animal and human medicine, there is no dividing line, nor should there be. The object is different, but the experience obtained constitutes the basis of all medicine." Well, I've become very interested and really almost mission-driven to bring the human medical community into One Health and planetary health. I've written popular science books, done a lot of research in academic publications, conferences, courses, trying to really bring together and accelerate biomedical innovation to benefit all species, although as a physician, I'm focused on humans, through this broadly phylogenetic and evolutionary informed approach. All right, so let's get to it. One major barrier that is, and it continues to be a barrier, but a barrier that I've been focused on tackling is a scientific blindfold, and that is the anthropocentrism that I talked about and human exceptionalism. And in medicine, medical human exceptionalism, there's many different definitions of human exceptionalism. It takes the form of assumptions about human uniqueness, really unexamined assumptions about the uniqueness of our vulnerabilities compared to other animals. And this overestimation of our uniqueness creates obscures certain insights. And in addition, there is really low awareness of physiologic biodiversity. So if you talk to most physicians, very intelligent, highly educated individuals who are knowledgeable about, issues around biodiversity, but if you ask them to sort of close their eyes and see envision biodiversity, and I've done this, almost everyone describes sort of drone photography over the Amazon. What I think is remarkable is that there isn't a kind of an internalization of the idea that there is this physiologic biodiversity within the fur and the feathers that really can be a source of opportunity. So to counter that scientific blindfold, to try to open eyes, I started these Zoobiquity conferences to bring together veterinary schools and medical schools. And this has been since 2011. So we'll have a veterinary oncologist and a human oncologist presenting cases of a glioblastoma, which is it's a human and non-human brain cancer. And they discuss it. The doctors, be they veterinarians or physicians, have this conversation about the disease, the natural history, the therapy, et cetera. Osteosarcoma, bone cancer in dogs and humans, cardiovascular diseases, infertility, and even some biobehavioral disorders. All right. So let's get to it. How exactly, with all of this, what I see as potential, I struggled and have worked hard to answer this question. What is the methodology? I mean, what is the approach? How exactly can we find animal knowledge to improve human health? And the answer is, let's start with a little bit of evolution and a few evolutionary principles that people are probably familiar with, but let's just review them. And of course, we're going to start with Nico Tinbergen, who, along with Konrad Lorenz and Carl von Fisch, won the Nobel Prize in medicine and physiology, right? In 1973. The three of these scientists were animal behaviorists, and yet they won the Nobel Prize in medicine. And of course, Tinbergen's most enduring legacy was this four-part structure where he sort of reconceptualized how we explain biological phenomenon. From Tinbergen's perspective, it was not enough to explain a biological characteristic with some mechanism or some statement about the developmental state. Rather, he felt one needed to look at what the adaptive benefit of that trait was. In other words, how was that trait fitness enhancing, survival or reproduction enhancing? And to do that required thinking phylogenetically. And of course, phylogenies are these family trees in essence that show us the relationship between species and their characteristics. You saw the one that I created in my little image. And of course, this is Darwin's sort of scribblings as he was writing The Origin of Species. And so this idea of a phylogenetic perspective really got into my brain and began to inform what I was doing. And remember, every time you draw a phylogeny, and they can be vertical, horizontal, they can be spiral, you've seen many of them, but ultimately there is a timeline, there is an x-axis that is going to show the history of life on Earth. And here we have 3.6 billion years over here in the present and here. All right. So if timelines are important, if when we're thinking phylogenetically, there is a past and a present. Let's start from there and look at the history, the past of life on Earth. So this is actually, we started with the Big Bang, and I'm going to run it quickly again. We started with the Big Bang 14 billion years ago, the Earth at 4.5 billion, the moon just shot off. But you know that, of course, we didn't have life on Earth until about 3.7 billion years ago, right? When we had single-celled organisms, aquatic only. There was the evolution of photosynthesis, and then, of course, this great oxidation event, which is one of the first extinction events, a couple of glaciation events. And then about 600 million years ago or so, we have multicellularity and triploblasticity. Essentially, the stage has been set for animal life, for metazoan life. And at that point, we go on. We, of course, have the Cambrian explosion, where 99% of the animal species on Earth today emerged. And we have this, incredible diversification, terrestrialization of life, of species. But I want to run it for a moment and stop right there. This is the end of the tape. And you can see the timestamp. There's the meteor. So we know that's 65 million years ago, right? And you'll notice on this image, we have only one primate. It looks like a common ancestor with one of the modern great apes about 25 million years ago. But of course, there are no Homo sapiens on this picture, and this group understands why. Because, of course, our 200,000-year-old species is much too recent to appear here. I show this when I present to physicians and medical students because I want to remind the group of the evolutionary principle of descent with modification. That if evolution works through descent with modification, we say that there's a species A, B, C, and D. Species B is different from species A, but very similar to species A, right? And species C is much more similar to species B than it is dissimilar, and so on and so forth. In other words, emphasizing similarity as opposed to assuming uniqueness, assuming dissimilarity. So another way of looking at this is if we think about life on Earth as an airplane trip from Los Angeles to New York, we've got life over New Mexico, we've got photosynthesis over Colorado, but it is not going to be until we are in Western Pennsylvania that we see metazoan species really begin. And then it's quite remarkable. We've got amphibians, we've got dinosaurs, the age of dinosaurs, we got dinosaur extinction, common ancestor with chimps. And here, 570 feet before touchdown in New York City, we appear. Again, descent with modification, a reminder of shared biology, right? Overcoming really centuries, millennia of human exceptionalism, that have had as the assumption human uniqueness. That's a whole other conversation, but I just wanted to set the stage. So now I've turned the state of Pennsylvania into the life of metazoans, right? The phylogeny of metazoans. And that is going to set the stage for the examples that I want to share. So the evolutionary principles, kind of the the general idea is that we can use phylogenetic models, we can use phylogenetic thinking to look for and understand vulnerability and resistance across the tree of life. Let's talk about vulnerability. All right. So this is an iconic cinematic device. It's fear fainting, right? You saw Kim Basinger, and then it was Judy Garland fainting. The medical term for this is vasovagal syncope, a more kind of common occurrence. You see it when people are giving blood, for example. That's what this video is of. It's common. It's 1 in 3 humans will have an episode of vasovagal syncope. And it's the most common cause of fainting in people who are under the age of 40. And very often it occurs when there is some intense event. It can be fear, it can be intense emotional experiences, pain, physical pain. And what we see is mechanistically, this intense experience, right? So something's happening, it's causing an exaggerated sympathetic, right? The sympathetic nervous system activation. But what we see is this bradycardia, which means a slowing of the heart, and vasodilation, which is an opening of the blood vessels instead of constriction. And that leads to fainting. Syncope is the medical term for fainting, right? So the blood vessels are opening, the heart is slowing, and there's fainting. Now, this is something that might be odd. And when I ask medical students about vasovagal syncope, they've been taught to say that it is paradoxical. Why? Because here are some guys who are in the running of the bulls, and what do you expect in a frightening situation is a fight or flight response and an accelerated heart rate, right? You expect what's called tachycardia, which you see here, this EKG. But what happens when individuals have this bradycardia, this vasovagal fainting, this fear fainting, is that the opposite happens. The heart rate starts to slow. Now, that seems paradoxical. It seems pretty maladaptive. But as you begin to, and as I began to, and this is one of the first projects that I took on, this is already 15 years ago, look across species for evidence of this autonomic arc, it suddenly starts to look less paradoxical. And in fact, one of the first phylogenies of vulnerability that I did was looking for what's called alarm bradycardia, which is the veterinary term for this slowing of the heart that you see with vasovagal syncope. And I sought across vertebrate lineages, right, from fish to mammals. So what does that mean? So when we have a conserved trait, here's another phylogeny, right? If we have a trait that we are seeing in mammals and birds and reptiles, amphibians and fish, one of the hypotheses is that it existed in the common ancestor. And if it existed in the common ancestor and persists, a hypothesis, it's not definitive, but a hypothesis is that it confers some fitness benefit, some biological benefit. But a medical student might ask me, but Dr. Natterson Horowitz, I mean, how can it possibly be biologically beneficial to suddenly lose consciousness? Maybe you're going to be standing at the top of a stairwell and break your neck or hit your head. What is beneficial about it? And the answer is, it is not going to look beneficial. It is not going to, there's not going to be no evidence of fitness benefit if you take an anthropocentric approach, if you are focused on only our species. But if you look broadly across species and see that it appears to be a conserved reflex, you can begin to look for some adaptive physiology, right? That's what Nico Tinbergen would have us do. And there's an adaptive hypothesis that I have developed, and I suspect is true. I'll show you the evidence for it. And that is the following. Many underwater predators hunt by tracking on the electrical signal from the prey. And they have these spicules on their faces to allow them to detect the voltage coming off of the prey. Remember that an EKG is a voltage time curve, right? So as the hunter is tracking his prey, if all of a sudden their heart rate plummets, it could render the predator acoustically blind, essentially. And that could be adaptive for the prey. In other words, that could be an opportunity to escape. And we actually know that there are some popular aquarium fish who will sort of quote unquote play dead. They're not actually playing dead. I doubt there's consciousness of this, but there appears to be this there's a bradycardia that can ensue when the tank is being cleared. But of course, those are fish. Let's talk about mammals. This was a study I found from 1979. A group of scientists put EKG leads on this young deer, this fawn. They then drove a Jeep near to where this deer was, and they put on the top a speaker, and they played recordings they had of wolves howling. The intent was to scare the fawn. And indeed, the heart rate of the fawn started at 180 beats per minute. But with these howling, with this scary noise, the heart rate plummeted to 30 beats per minute. This was a bradycardia. And the resulting physiology is one of tonic immobility. Now, how might that be adaptive? How might that be fitness enhancing? And most of my students begin to develop hypotheses around anti-predation benefit, that being still, perhaps it's a way to hide. In fact, this video, I'm going to just set it up right before I play it. In the video you're about to see, there is an impala that has been taken down by a young cheetah. But then a mature hyena comes and bullies the sort of takes the spoils of takes the impala from the cheetah, and that's where we're going to start. So the spotted hyena is digging in, but the cheetah is returning, so the hyena is going to chase it off. Now I want you to focus on the impala, not the hyena. Okay, so I can't prove that there was a bradycardia. However, I do believe that the tonic immobility in this case was life-saving, and therefore, if we can assume that there is an autonomic neurophysiology in this animal, that has adaptive benefit. It has survival, anti-predation benefit. All right, that was vulnerability example number one. I promised you another vulnerability example around breast cancer, and here it is. I became really interested in focusing on female health about was probably 5 years ago or so, or it was around the beginning of the pandemic, and I created this initiative, Female Health Across the Tree of Life, because of course, not only is the field of medicine, we have a long-standing tradition of anthropocentrism, we also have a pretty miserable history of androcentrism, with female health research being very ignored in many cases. So we have a lot of catching up to do. And that's how I came to do this Female Health Across the Tree of Life, the Sisterhood of Species, and engage with Ask Nature. All right. Let's talk about breast cancer quickly. It is 1 in 3 new cancer diagnoses in women. It is increasingly tied to environmental factors. This is of great concern. Now, everyone's familiar with the canary in the coal mine, the idea that if you bring a small animal that shares vulnerability to something in the environment with the human, that they will present the symptoms earlier, and therefore you'll be tipped off to the presence of the danger. Well, there was an example of this in the St. Lawrence estuary between 1983 and 1999. There's been a stable population of beluga whales living in this estuary for hundreds of years. But between these years, wildlife biologists noticed increasingly that there were deaths. There was a near epidemic in terms of the numbers of deaths. And when they were doing necropsies on these whales, they found that over 25% of the females had died from either mammary or ovarian cancer. And this is unusual for cetaceans. Cetaceans do get cancer, but their malignancies are generally hematologic, like lymphomas and leukemia. So this was unusual. And it will not be a surprise to anyone to learn that, in fact, this epidemic essentially was traced to these aluminum smelting facilities that were upstream that were just spewing out polyaromatic hydrocarbons and whatnot. And of course, the human communities, the coastal communities, women were also being affected. So this is another way in which we can begin thinking in a broadly comparative way, open our eyes to this idea that we are not the only species on the planet, and that can impact human health. But I want to really focus on resistance. And Andrew, is it okay if I give myself 10 minutes?
Absolutely.
Okay, so let me get into resistance. Now, Remember how I showed you the phylogeny and I said, hey, if you have a trait that exists across a wide range of taxa, as we see here, then we can hypothesize that the common ancestor may have also had that trait and that there's biological benefit. Okay, that's what I call the outside-in approach to understand vulnerability. But we can also flip it and look at a phylogeny from the inside out. In other words, to look at speciation, diversification, really looking at all of these new lineages and really break down the story of why and how those lineages emerged. And again, this is a highly informed group. I'm talking to Ask Nature community. So we know that changing environments shape phenotypes. We have the emergence of novel phenotypes, which when that phenotype is aligned or well aligned with the environment, and by that I mean has characteristics that allow it to counter existential threats, but also has characteristics that allow it to really leverage the resources in the environment. When that happens, those are successful phenotypes. And because environments shift so much, that becomes sort of the mother of this biodiversity that we see. And as I said before, biodiversity is not just on the outside. Biodiversity, from my perspective, for the world of biomedicine, physicians, medical students, all of us, includes physiology, biodiversity of physiology. And of course, when there is a diversity of physiology and there are animals living in environments where there are threats that they need to evolve adaptations to counter those threats, we see macroevolutionary innovation. And sometimes, of course, we can find characteristics that may be relevant to high-impact human health issues like cancer. I'm not going to spend much time on cancer at all, other than to say this is probably, I think looking for cancer resistance in other animals that is the farthest, most progress has been made with this approach around cancer. But I'm a cardiologist, and so we're going to talk about heart failure, because heart failure, humans have, this is an American statistic, 1 in 4 lifetime risk, but it's probably similar around the world. And there's a form of heart failure called heart failure with preserved ejection fraction, which is rising faster than any other form of heart failure and has become the most common cause of heart failure in women. So for short, we call it HFpEF. All right, so I'll call it HFpEF. And in a really simple summary, you have a normal looking heart here, right? So this is the back half of it. This is the left ventricle and the right ventricle. But if a person has high blood pressure, right? So that the left ventricle has to work really hard. Any muscle under pressure, right, is going to thicken. And what happens with HFpEF is that the left ventricle gets thick, but when it gets thick, it also gets stiff. It develops fibrosis and other cellular changes that make it difficult for the heart to relax and leads to heart failure. In my human patients who have longstanding hypertension that isn't treated, they do develop these very thick ventricles that have lots of fibrosis and they're stiff. And those patients, like this woman, find it very hard to, as it gets more severe, to even go from maybe their bedroom to their kitchen without feeling short of breath, let alone go up a flight of stairs. It's very debilitating and a cause of death. So the question is, are there evolved adaptations in other species that may have solved this issue? And of course, the giraffe becomes a natural candidate. Why? Because giraffe have the highest blood pressure of any animal on Earth. And the reason for that, of course, is the location of the left ventricle relative to the brain, which it must perfuse. That can be up to 3 vertical meters. And that pressure is significant. But of course, the selective advantages include access to food and, of course, scanning the horizon for predators. So, but if those selective advantages came at the cost of shortness of breath and poor exercise tolerance, well, for a prey species, that would not be possible, right? So and actually, let's just take a quick look. These are giraffe ventricles, all right? Look at how thick the giraffe ventricle is, right, compared to the human, with a tiny little cavity for the blood. This is very thick, but it's normal for a giraffe. In humans, we see high blood pressure, thick ventricle, and heart failure and death. But in giraffes, we see this high blood pressure, not abnormal. Remember, that's normal for them, evolved adaptation, a thick ventricle, but they are able to run up to 40 kilometers an hour multiple times per day. And I sat and I looked at this. It was probably about 7 years ago when I first became very interested and then preoccupied and then obsessed with how this was possible. And so this is really, this is what kind of motivated the entire project. Here's the story. Giraffe and the modern okapi are the two remaining extant species of Giraffidae. They shared a common ancestor about 11.5 million years ago. Now, the ancestors of the modern okapi moved toward the Congolese rainforests, where a longer neck there wouldn't be selective advantage to a longer neck. But of course, the giraffe species migrated to savanna, where the longer neck had selective advantages. So this is an opportunity for us because we can compare the genomes of these animals one is not long-necked and one is long-necked, to see, can we find what cardiovascular adaptations might allow this giraffe to have a thick ventricle, but not a stiff ventricle. For this giraffe to have essentially a ventricle exposed to high blood pressure, but no heart failure. And so I published this, and then a few months later, this wonderful paper came out from a group in China where they looked at the genome of the okapi and the giraffe. They focused on a gene called FGFR1, which is involved with cardiovascular function, and they did the following. They CRISPR'd the giraffe FGFR1 into mice. And then they compared them with a wild type mice. They infused a medicine, a drug that causes high blood pressure for 28 days in both. And then here's what they found. In the giraffe group, there was exceptional resistance to hypertension. Here's the blood pressure in the mice with normal mouse, FGFR1. Here's the giraffe. There was significant suppression of fibrosis. Here is the giraffe, minimal fibrosis. Here's the non-giraffe, lots of cardiac fibrosis like we see in humans. And again, you see very little fibrosis, lots of fibrosis. So this is exciting. This suggests that we may, if we can identify evolved adaptations that have solved high impact issues in cardiovascular disease that are relevant to humans, if we can identify those adaptations and the specific genomes that are responsible for those adaptations, we may be able to use gene therapies and other modalities to bring that knowledge into human medicine. Now, I'm not saying that this is the singular explanation for the giraffe's physiology, but it's a beginning. It's an invitation. Very quickly, I'm going to take just 3 more minutes and then we'll be done and we'll talk. Gestational hypertension, right? So that means during pregnancy, high blood pressure. Preeclampsia is a form of gestational hypertension, and it is a leading cause of both maternal and fetal mortality, very common, and a huge focus of research interest. Well, if giraffes have these high blood pressures compared to humans, and if they have therefore evolved adaptations to prevent heart failure, to allow them to have thick ventricles, but not stiff ventricles, then there are many adverse effects of high blood pressure on the human body, and one of them happens during pregnancy. And so my hypothesis is that there must be in the pregnant female giraffe evolved adaptations that protect her, mother, and fetus from hypertension. And so there's an opportunity to look at that. Other issues in women's health, osteoporosis, which affects 1 in 4 women over the age of 65. It's a very important functional limitation issue. And essentially, here's healthy bone, normal bone structure that's compact, and here's osteoporotic bone. It's kind of spongy. One of the reasons that osteoporosis occurs is a lack of estrogen. So if women, when they're ovulating, in the age group when they're ovulating, if they, for a variety of reasons, stop ovulating, they lose the monthly estrogen that helps keep bones strong. And one of the thoughts that I had a few years ago, well, how do animals who are monoestrous, in other words, only ovulate once a year, right? We ovulate 12 times a year when we're in reproductive phase of life. How do animals who are monoestrous, for example, like the panda, how are they keeping their bones strong? And so let me just give you one hypothesis that I have, that perhaps it has to do with their dietary intake. In the wild, 99% of their dietary intake is bamboo, of course. And bamboo is a powerful source of a number of sources of phytoestrogen. So the flavonoids and these lignans, which are metabolized into a kind of an estrogen precursor. So this is a possibility. I don't have evidence for that. But while we're talking about pregnancy and while we're talking about female animals, I just want to wrap things up by turning your attention to the absolute the incredible athleticism of pregnancy in wild animals. And I'm focusing just for a moment or two on predator and prey animals. So here we have, I guess that's a springbok who is clearly pregnant. And if you know about, the behavior of fleeing springbok, you know that they do this pronking, this starting, they jump up and down. And a pregnant animal, for example, a pregnant giraffe, in the final weeks of her pregnancy, she's carrying hundreds of extra pounds of fluid and fat and fetus, and yet she cannot be the slowest animal in the herd. If that was the case, she would be picked off every time. So there must be some athletic adaptations that allow prey animals to maintain a degree of the ability to evade predators. And of course, the other side of that equation are the predators themselves in the final months of their pregnancies. They have increased caloric requirements, and so they must have evolved athleticism-related adaptations of pregnancy. I can tell you in the final days of my own pregnancies, I was on call. I was winded walking to the elevator. So I think this is can be a source of knowledge and inspiration for human pregnancy. I'm going to wrap things up with two quotes from two of my scientific heroes. The first is Rachel Carson, who, of course, she's my hero for a number of reasons. She launched the modern environmental movement, of course, but I love this quote from Silent Spring: "In nature, nothing exists alone." This is something that I share with all of my medical students and anyone who will listen, because it really applies to the health of humans and other animals. And finally, if we're talking about turning to the natural world as a way of accelerating bioinnovation, there's plenty that, we look at what has the revolution in biology over the last 25 years. It's been spectacular and awe-inspiring. However, there are many intractable challenges, and we need new approaches. And no one articulated the approach and the reason for the approach better than Darwin himself, who wrote in The Origin, "Natural selection is a power incessantly ready for action," and this is my favorite part, "and immeasurably superior to man's feeble efforts." And with that, thank you for listening, and let's have a conversation.
Thank you so much, Barbara. That was wonderful. So everyone, you can use the Q&A button again down below to start asking your questions here, and we'll tee these up and get you ready to be able to ask on screen here. And we'll kind of jump in here. And we have a couple ready already. But I want to say, first of all, again, thank you, Barbara. We've really loved following your work for several years and helping to bring it to people and to explore it, see new stories, and even to understand ones that we've been through before with deeper level and greater perspective is just really a treat. And I love all that you're bringing, not only in representing our connection, bringing the rest of the animal species into our sense of health, and it also brings us into with them. And I think, one of the negative sides of anthropocentrism sometimes is that then people start to feel that disconnection, that alienation, like, who are we? Why are we here? Are we, and then through this lens, you really see how we are just one member of this really not only diverse family, but really close family. And that timeline makes you just really viscerally aware of how close we are. We are not distantly related to the other mammals here, especially, let alone anybody else. Let's start off here with some of the questions here. Doreen, I see that you have a question and are ready. Why don't you come on screen? You can unmute and come on and ask your question.
Hi, thanks, Andrew. Barbara, wonderful, wonderful presentation. I am a first-time attendee and first time hearing about your research, and it was so well presented, as were your findings. And I'm curious, with the advent of AI and discovering these collaborators and past research, are you and your fellow collaborators continuing or looking into using applied AI to probe the rich history of, research findings across species?
Yes, I mean, it's almost like I set you up to ask that. Absolutely. So there, I decided, I read a paper about how you can use neural networks to, to take knowledge graphs and really, to show links between knowledge graphs. And I thought, wow, this is something that could be used to identify sort of phenotypes that may have adaptations that are relevant to human health. So I know that there are a couple of companies that have AI that are sort of AI powered and looking for innovation. And I've been working with some graduate students actually to develop a convolutional neural network to identify, we're not very far, but to identify specific physiology that may be relevant to, I'm not going to say what the two diseases are, but yes, that is something very exciting. And the other piece of the kind of, I'm going to call it the computational revolution, is just the number of fully sequenced genomes that we have. So Andrew, when you were saying that, we talk, I mean, I call it the blindfold of human exceptionalism. And when I give talks to groups of psychiatrists, I talk about it because there's real resistance to thinking about linkages between animal behavior and human behavior. Everybody feels it's required that you say up front 10 times, we're not going to anthropomorphize. We're not going to anthropomorphize. It's like there's this tremendous concern that that's like scientific error number one. And I would say if since 2005, right, since we've had the full human genome, we have this exponentially growing number of species where we have fully sequenced genomes and we have very sophisticated ways of comparing them. We know, by the way, I believe that there's the Earth Biogenome Project plans on having like 1.5 million eukaryotic species sequenced within a decade. And looking at the zebrafish and psychiatry, you've got, I think, 80% or 85% of the genes that are directly implicated in human psychiatric diseases. We're talking about depression, bipolar disorder, schizophrenia, autism. There are full orthologs in zebrafish, a species with whom we shared a common ancestor over 400 million years ago. So I think this concern about anthropocentrism, about anthropomorphizing, needs to be updated scientifically. We need to have as our default hypothesis, our default assumption, our null hypothesis needs to be inverted. And we have to assume commonality. The science is telling us we need to assume commonality. And then, of course, we're going to find differences.
That's great. I love that one. And I think of that sometimes where you see some of these behaviors and you're like, it's not anthropomorphism. It's actually been like this, almost like this greedy, like claiming of territory. And you're like, because it's things like this. Well, could that animal really be caring for its young? You're like, that's kind of anthropomorphizing it. And you're like, oh, really? So you think that humans have exclusive domain to caring for your offspring? That's okay. So, all right, we have lots of great questions coming in. So let me come now to Michelle, if you would be ready to ask your question.
Hi. Great presentation. I'm very intrigued about the evolution myself, about especially in the immune system. But speaking about the giraffe, as you mentioned, I read a paper about how giraffes' ligaments on their necks actually have higher amounts of elastic fibers. So I was wondering if like some tissue could be just like I guess have some multiplex spatial bioimaging that might actually highlight to see if there's an actual larger amount of elastic fibers in the heart of the giraffes as well.
Yeah, it's such a great question. And I mean, there are a number of people who are looking at all kinds of, I mean, the physiology of the giraffe is so interesting anyway. So people have looked at adaptations at the renal level, at the pulmonary artery level, vascular smooth muscle. So yeah, I mean, it just keeps growing.
Great. And so there's another animal example that we didn't get to speak to yet, but Rashida has some question about flamingos. So Rashida, if you're ready.
Thank you. Thank you so much, Doctor, for the wonderful presentation. It was truly a new learning experience for us. I've just recently been studying flamingos, so one of my projects that I've been doing. So in that, I have come across the fact that, and of course, I've watched flamingos also in my city, Mumbai, in India. And they have this gregarious kind of community and they always stay together. So I was wondering whether that, even when they are pregnant, like they are always pregnant in a group. So would that in any way affect the health issues? And is there any kind of study done to see whether they are helping each other when they are sick? Or even do they have a consciousness when they are ill? Do they realize they are not well?
So that's such an interesting question. I don't, so you're asking in egg-laying species, do the females kind of, are you saying, are they grouping together when they are in the egg-laying phase of,
Yes.
of life? I don't know. I don't know enough about the life history of flamingos. What is interesting, you asked about health behaviors and helping behaviors. We know that there are health helping behaviors. I mean, of course, there was the controversy at one point a long time ago. When I was in college, by the way, we were told that chimpanzees were the only animals who used tools. And then I guess whenever it was 10, 15 years later, they began realizing, no, that's not the case. And now, of course, we know that fish use tools and even some invertebrates. Then it was, humans are the only animals that have complex language, right? And then, of course, that gets to be. And then there's the mirror test, right? Self-recognition. And then, of course, it expands to include fish. So anytime there's a criteria of what makes us uniquely human, it tends to be debunked. And one of these was helping sickness helping behaviors. There's a term for it, I can't remember, and including pregnancy and delivery. But we now know that that there is assistance given in other primates, right, during childbirth. Not just in our species. So I don't know about in flamingos and in birds in general.
There was one more species which was very interesting is the octopus. It has blue blood. Is there any research on that? And is that a different evolution altogether because it has 3 hearts, I suppose, and it's a blue-blooded creature. So is that a different phylogeny or?
Right. I mean, yeah, that's cool. Right. That has its own fascinating biology, as do, I mean, the cephalopods have their own. I mean, if we could do a whole session on the color of blood of different species and what the significance of it, and all of it ties back to human health. It can if we want to think of it that way.
As a content guy, I would say The Color of Blood is a fantastic title, and that will do great. We get lots of great conversation, and people will be excited about that. I've got a question here that I'll read for our one of our participants, Molianne here. She says, as a biochemist, my focus is on understanding the biochemical mechanisms for adaptations like those that you've mentioned. However, funding for this sort of literary research is difficult. How do you find your research? And how would you suggest that others go about funding the time and effort that it takes to research and publish these sort of inquiries and findings?
Thank you for that question, and I share your concern. One of the challenges, and we are having people who are doing this kind of research are having conversations about making this approach, and I'm going to assume that you're talking about finding evolved adaptations that have salience for human health, is creating a language that funders are familiar with. In other words, sometimes when I'll write a grant, I have to use so much real estate to just explain the concept of an evolved adaptation that has solved the problem. It is, we need to get to the point, and it's a goal of mine to get to the point where there is familiarity with this approach. Once there is the killer app, right, that changes everything, then it will quickly become very familiar. But until then, and to get to that killer app, so one of the opportunities, the challenges that we all have right now is to develop language writing and publish on this approach in ways that that resonate with other researchers who are doing traditional biomedical research. And also becoming expert on framing the question in a truly translational context, that is connecting it back to some high impact issue in human health, particularly issues that have been the focus, have gotten a lot of research attention and funding, but where there still is, there's a bottleneck. So it's important.
We're definitely count us as partners for you there, Barbara. With Ask Nature, that's our whole idea, is to take this deep knowledge of the way that organisms are working and functioning and make that accessible to everyone, so that from whatever field they're coming, so that knowledge can be translated and applied into all of the fields that we think that it can be through the practice of biomimicry. So that's really, it's an important lesson about the whole thing, is that nature is just out there. The language that we use to describe it is all just one thing that we've done, but the biology itself is just out there occurring. And if we can present it in accessible ways, then people from all walks can learn from it and apply it. We have another question from the audience here, or from the community here. Mark, if you are ready, go ahead.
Thanks, Andrew. I'm also looking forward to reading the book on blood color. Yeah, thanks, Barbara. Yeah, very specifically, my question: what general patterns, or perhaps even universal patterns, have you found in studying mammals that you think are most important for humans to be understanding and being guided by, and what we're doing for human health as individuals and communities, and ultimately humanity and our relationship with all of the living world system?
You're asking me to select one, and I can't, but I'll tell you one that I think is one of many that I think is really important and has been absolutely overlooked. And that is the selective pressure of mammalian pregnancy and how it has shaped the modern human phenotype. So right now there's a lot of interest in sex differences, right? And some of that is because research on women was ignored for so long. I mean, I shudder when I think that in 1993, I just finished all my cardiac training. I was like a young professor, and I had no idea, zero, that the studies that I was using, that the NIH did not require women to be in the clinical trials. Their funded investigators didn't have. So all of these medications I was prescribing, devices, the studies, I thought I was being so academically shrewd, being evidence-based, but women were a part of it. And there was this assumption that women were sort of smaller men and all of this. So it was ignored. But when you think about where there would be significant selective pressure in shaping phenotypes, I mean, in mammalian pregnancy, you're going to have a huge amount of selective pressure. You think about the reproductive investment, think about that what it was, Springbok at the end of a pregnancy, right? So pregnancy, and as a cardiologist, I know that the pregnancy is one of the most, if not the most, active. it is an athletic experience for a female. By the beginning of the third trimester, a woman's circulating plasma volume is expanded 40%. 40%. And her cardiac output, which is the stroke volume times the heart rate, so it's how much blood she's pumping, has increased per minute, has increased 50%. In order to accomplish that, the mass of her heart increases 20%. It's something called cardiac remodeling. The cardiomyocytes change, they're metabolically, the cellular, subcellular, the geometric, anatomic, it's massively changed. And then following delivery, it reverse remodels. Now, this is a pressure, a physiologic pressure that is not being imposed on the male myocardium, the mammalian male myocardium, right? But it is being imposed on the female myocardium. And so you end up with, my hypothesis is that you end up with two separate cardiac phenotypes. Of course, what I'm saying about the heart can apply to other organs. But now, with that knowledge, let's fast forward back. Let's go to the NIH next week, where there's a conference on cardiovascular sex differences. You can have a conference and have a huge amount of excellent research presented that is very mechanistic, identifying, the difference, estrogen differences in calcium channel, velocity, blah, blah, blah. But until you realize that that pregnancy was a selective pressure that shaped these phenotypic differences, you're flying blind. As soon as you know that there's it changes how you understand everything. And so there's this concept in evolutionary medicine of a trade-off, right? So that you have a selective pressure that leads to an adaptive phenotype, but that there's some maladaptive element of that phenotype later in life. That is what we're looking at when we see this 9 times higher incidence of certain forms of heart failure in women. When we see anyway, the point is that I think that if we could focus on pregnancy and begin looking at pregnancy in the wild, and what are the selective pressures, there is no information on it, none. You think about all of those wildlife videos that you've seen since you were a child, those documentaries, staring right at us has been one of the life history events for which you would predict there would be so much selective pressure in shaping phenotype, and yet it's been ignored.
Wow, well, ignored no longer, Barbara, through this amazing work that you're doing. Thank you so much for joining us today, Barbara, and everyone all around the world. It was great to see this community coming together. The conversation will continue in the Ask Nature Hive. So if you are not a member yet, watch your email from attending here. We'll be emailing everyone out with an offer to join the Ask Nature Hive, which is our new online community. It's a buy one, get one. So you could team up with a friend who's here or invite someone else to join you. And that offer is good through the end of the year. And then going into the new year, we're going to have a really great lineup. And the first 3 that we've got teed up here are some really wonderful people. T.H. Culhane is a National Geographic explorer who's working using biomimetic and other technologies to really put the kind of large-scale conversion of our technologies into practice on a small scale with like homemade biodigesters and everything, where you're taking kitchen scraps and turning it into fuel in remote areas and impoverished areas and really revitalizing communities. We'll be talking, that's in January. In February, we've got Heidi Fisher, who's a well-known figure in the biomimicry community. And if you've never met her, you're going to love hearing from her as well. She's been focusing on biomimicry of the national parks. That also ties in with some Ask Nature features that we're working on with Heidi. And she's been visiting the parks, doing a real deep dive, getting to know the areas, the plants, the animals, the ecosystems, the balances among them. And she'll bring the first couple of those to life. And we're looking forward to that becoming a more widespread way of documenting and engaging with the national parks. And then in March, we have New York Times columnist Carl Zimmer, who has a new book coming out, Airborne, The Hidden History of the Life We Breathe. And this is really exciting. This stems from the research he was doing in the coverage around COVID and its spread. And he discovered just how much life there is floating in the air all around us, and the air around us eventually ends up inside us. And so this really dynamic biological story of the very air that we breathe and the air that rises miles and miles above our heads. It's a really amazing story that he's going to explore with us. So that's just the first 3 months. We're going to have a whole lot more. And beyond the monthly scheduled speaker series, we have more informal meetups and other events that'll be happening in the Hive. So watch your emails, join us there. Continue to post questions for those of you who are already in the Hive. For Barbara is now a member as well, and will be in there and able to respond and engage with us there. And we really look forward to everyone on the next one. And thank you so much for joining us here today. We are really, really happy with this engagement with the community and seeing everyone come together around these really amazing topics presented by really amazing people and speakers. So thanks again, Barbara, and all the best to everyone. Thanks all, and a Happy New Year as it's coming.